Title is Cosmology from the Moon, the Dark Ages Radio Explorer mission. Thank you.
Great. Thanks. Could we get the animation started on that too, please? Great. Thanks, Chris. One of the last frontiers in modern cosmology is the time period between the so-called dark ages and cosmic dawn. This is when the first stars, the first galaxies, the first quasars, accreting black holes form. It's a really fundamental time period in the early universe, yet we effectively have no observations of this early time period. The reason is that these first objects are extremely faint. So even our best telescopes, such as Hubble and the upcoming James Webb Space Telescope, will be unable to detect these first objects. But there is a way to probe this time period, and that is to use the collective effects of these first stars and galaxies on the intergalactic medium using the so-called global signal. The trick here is to look at that impact on the intergalactic medium, which is composed mainly of neutral hydrogen, and neutral hydrogen emits a hyperfine line at a rest wavelength of 21 centimeters, 1.4 gigahertz. Now, because we're looking at very high redshifts, that frequency has shifted down to a much lower level below 100 megahertz. So in order to do these radio frequency observations, they have to be done using techniques of very low frequency radio astronomy, and that requires a very quiet environment, which does not exist on the Earth. The Earth is polluted with radio frequency interference, and also the ionosphere is a source that prevents the signals from being detected due to emission, absorption, and refraction. So the moon, particularly the far side of the moon, is the ideal place in the inner solar system for these observations. So to get this started, we've proposed a mission called DARE, the Dark Ages Radio Explorer, which would be an orbiting spacecraft in orbit of the moon, and it takes data only above the radio quiet far side. So here's a little bit more on the science that we will perform. On the left-hand side, here's a cartoon picture of the evolution of the early universe, Big Bang at the top. Today's universe down at the bottom, 13.8 billion years later. And different epochs are indicated. CMB is the cosmic microwave background. This is the beginning of the dark ages. At this point in the early universe, the universe literally is dark because it's before the first stars and galaxies. But the cores of those first stars are collapsing, and at redshifts of somewhere between 20 and 30, time periods of roughly a few 100 million years after the Big Bang, those first stars will turn on. Now, theory predicts those first stars to be very massive, roughly 100 times the mass of the sun. They will emit prodigiously in ultraviolet, Lyman alpha, and they will ionize a sphere around them of gas. What you see here on the right-hand side is a numerical simulation of this early universe from my colleague John Wise within the cosmic web. And these light blue regions represent at the center where those first stars form, and the light blue regions are the expanding ionized gas cloud around those first stars. As this progresses, more of these stars turn on. Astronomers have come to call this now the cosmic dawn time period, and this will continue such that these ionized cloud regions will begin to overlap, and they will cause the universe to go into its last phase transition from what was an all-neutral intergalactic medium up over here to today's observed all ionized. This is the period that astronomers call the epoch of reionization at a redshift of about 6, roughly 1 billion years after the Big Bang. So what we're probing with DARE is this whole region over here, which, as I said before, virtually has no observations, and we're pursuing these science questions related to the first stars and the first galaxies. The way we're going to do this, as I alluded to before, is using what's called the global signal from 21 centimeters. And here's a theoretical construct from our theory team with DARE. What you're looking at here is a slice of the universe going from early times to later times up over here closer to the modern era. The color coding is blue is neutral, intergalactic medium gas, and red and black are heated and ionized gas. Down at the bottom is the theoretical spectrum. This is power measured against the CMB versus frequency. Now, because we're using a spectral line, a 21 centimeter line, each one of these frequencies actually corresponds to a redshift. So the really powerful technique or tool that we have here available is that by sweeping through the frequency, we're actually sweeping through the different epochs or the evolution of the universe. According to our theoretical constructs, there are definite features that are expected to appear in the spectrum. We call these turning points. The first one of these, turning point B, corresponds to that ignition of the first stars. As I mentioned before, Lyman alpha ultraviolet light is produced from those first stars. It couples to the hyperfine transition of neutral hydrogen, causing the signal to go from this state into a deep absorption trough. Where this turning point occurs in frequency is going to correspond to the redshift of when the first stars turn on. So with this simple measurement, we will for the first time be able to constrain models of when those first epoch of stars turned on in the early universe. Similarly, down over here, turning point C corresponds to heating by the first black holes. These are the remnants, probably, of the first most massive stars. The accreting black holes, they produce X-rays. The X-rays heat the intergalactic medium and drive the signal from absorption into emission. Where that occurs, once again, that frequency and therefore the redshift will tell us for the first time when those accreting black holes turned on. Finally, we have turning point D. This is the onset of reionization. At this point, the universe is mostly neutral. About 90% of the intergalactic medium is neutral. And when this ends at redshifts of 6, virtually the entire intergalactic medium is now ionized. So this will tell us for the first time when the reionization began. Now, to give you some idea of what we're attempting to measure, here are the anticipated error bars from DARE in red. These are actually the 90% confidence intervals. And shown also are current range in models of the first stars. In blue, we have between dashed and dotted here a factor of 100 difference in the uncertainties in the first star models. And in green, from dashed to dotted, a factor of 100 uncertainty in black holes. You can see that virtually those models right now are almost unbounded. But with the relative accuracy of DARE, we're going to be able to constrain not only the time scales, but also the nature of those first stars. So not surprisingly, this was identified in community surveys as important physics for this decade, particularly the cosmic dawn was identified as one of the top 3 priorities in the Astrophysics Decadal Survey. More recently, NASA Astrophysics headquartered did a division roadmap, and they identified one small mission, and I quote from that roadmap, mapping the universe's hydrogen clouds using 21 centimeter wavelengths via a lunar orbiter observing from the far side of the moon. What DARE, we're going to realize this mission, and we'll be able to answer this question, or begin to answer this question posed in the decadal survey: what were the first objects to light up the universe, and when did they do it? This is our project team that we have here. We have a great group of individuals and institutions who are participating in this. This mission was submitted, by the way, to NASA's Small Explorer program late last year. We're under review at the moment. So the group is led by my home institution, University of Colorado. Here at NASA Ames does the project management as well as mission operations. JPL will be involved in building the science instrument. And then finally, Ball Aerospace will be building our spacecraft. So here's our baseline mission concept, just to give you a quick overview. We will be in orbit for 2 years. We will obtain a little less than 1,000 hours of data in which we will be in the quiet zone. That is, we will be occulted from both the Earth and the Sun, because the Sun may also be a source of interference at these wavelengths. The instrument I'll talk a little bit more about in a moment. We are proposing to launch in late 2020. We're also proposing to launch as a secondary payload on an Atlas V. This is the first time the Astrophysics Division has allowed secondary payload launches, and we're taking advantage of that. We're launching the GTO and then go into a lunar orbit, a 125-kilometer circular, nearly equatorial orbit. This is a picture of the spacecraft. This will be the fourth build of this spacecraft by Ball Aerospace. Our antenna is shown at the top, these bicones, unique antenna design. These radials sticking out over here serve as a ground plane to help shape the beam. Also shown in a cartoon version is how DARE fits inside the fairing of an Atlas V with a yet-to-be-determined primary. We've got good performance margin for the spacecraft in all areas, including electromagnetic interference. We have a buttoned-up Faraday cage that gives us 100 dB of shielding from our own instruments so that they don't interfere with our observations. Here's a science instrument, a quick summary of the science instrument. Once again, you see the bicones, which are deployable, spring-loaded, deployable to 3 meters. We also have a pseudo-correlation receiver, which has good flight heritage on a number of planetary and astrophysics missions, and also a high dynamic range spectrometer. The performance of the instrument is shown up over here, our uncertainty versus frequency. The design capability is actually down here in blue, but we added a 50% margin onto the science instrument, and that's shown in our baseline in black. In fact, it's that baseline that the errors I showed you earlier on the spectrum were designed for. So we're in pretty good shape in terms of performance margin. Now, the most difficult part of this mission, even in orbit of the moon, where we're free of radio frequency interference and ionosphere, is still the galaxy. We're having to look through a foreground which is 3 to as much as 6 orders of magnitude greater than the signal that we're looking for. Now, that's not too much different than what the CMB folks are facing on a pretty regular basis. In fact, we're going to utilize some of the same techniques to be able to pull out that signal in the presence of the foreground, namely Bayesian statistical approach, particularly using a Markov chain Monte Carlo technique. We've developed some elaborate simulation codes to model this. This is one of the latest from a paper we're just getting ready to submit to the Astrophysical Journal with my student and former postdoc. What you're looking at here is what we're going to be able to do is we fit simultaneously to the foreground, the instrument parameters, and the parameters of the first stars and galaxies, and looking for the best fit. This is an example of one of those simulations that we've done here. And what we're able to pull out is to bound, for the first time, the mass properties of the first stars and galaxies, and also their energy output in their spectra for that first generation of stars, black holes, and galaxies. That's pretty exciting. Once again, we have virtually no data on these characteristics right now, and they're extremely important in understanding how we got from that very early universe to the objects that we see today. So to summarize, and as part of that summary, I have a little video over here on the right-hand side. Maybe we could can we turn the lights back down, Barbara? Just flip that off. I think they'll show that a little bit better. This video is actually put together by our staff at the Fisk Planetarium in Boulder. So this is, the projection is actually made for a planetarium dome. So it looks a little strange as it's coming around, and that's because of the geometry of the dome. But it gives you some idea of what the spacecraft looks like in orbit of the moon and our instrument. So the goal is to address these science questions, which you see listed up over here. When did the first stars ignite? What were the properties of those stars? When did the first black holes turn on? What were their characteristics? When did reionization begin? And there's some interesting potential surprises coming out of the dark ages that we could investigate, for example, dark matter decay. And we're going to do this using the techniques that are indicated here. As I mentioned, and is shown here at the very bottom, we submitted this to NASA Astrophysics as a SMEX proposal in December and are awaiting the results. Thank you.
So we've got enough time for one quick question.
Sounds like a fantastic mission. I wish you the best of luck on being selected. I have a science question. You're looking at profiling different absorption features more or less by scanning your beam over wavelengths?
Right.
Okay, so there's different features to look at. How do you handle the mixing problems? How do you get a robust solution when multiple signals are mixed together and you're trying to tease out each of the signals, or will they not be expected to mix together, as you pointed?
So what we will do is we will actually produce this spectrum, and then what we will do is we will model the results from a large range of different predicted astrophysical models, and as I said, compare that with between the data and the model expectation to arrive at the best fits to these turning points.
Okay. One other quick question. So there's 1,000 hours you get of your observations.
Right.
But you leave many hours to look at something else. Are
Right.
you looking at the moon, perhaps?
We're going to look at the sun.
At the sun.
Yeah, so the sun is very interesting and is virtually unprobed at these wavelengths. So we think there's good evidence of microbursts on the sun that may be associated with magnetic field reconnection events on the sun. That's never been studied. So during that time period when the sun is up, we're going to be taking data there.